right, a little more accurate probably than what you can determine in your flammability diagram or using those equations, but you may not have tabulated values for what you need. So it's important to know how to do this. And really, right, if more people out there working with flammable liquids really were comfortable in doing this, I think we would be a whole lot better off, right? If people were realizing, if you saw that latest the Chevron Richmond fire, it's just baffling how they the first thing that they were aware, or someone in the company was aware of the fact that the tubing is thinning because of the light gas oil, right? Sulfur laden and all that, it will corrode the pipes. So someone in the organization knew that. It's questionable whether the people working on there, the volunteer firefighters from the company, whether or not how much they really knew. But that's information that is really important, right? To make sure it gets distributed. Because they were up there working on the pipe while it was in service, instead of shutting down the plant, right, or this tower. They decided to keep working on it, and even after the first, they opened up a bigger leak, and that didn't prompt them, right, to shut down. By the time they decided to shut down, it was too late. It opened up, and then, right, the rest is history. There's nothing left of the plant, or at least not that unit of the plant. Right. And we've seen explosion damage, right, so that everything near that explosion site is basically just ready to go to the dump, right? There's nothing left of it. So when we're working with these things, also what you're going to be faced with is not only, right, determining, okay, it is time to shut down, we need to do this safely, but now you have a vessel that contains flammable liquid or flammable gas. So you need to determine also how to take it out of service and back into service safely. And you have the tools here, right, by determining out of service fuel concentration. So that's you need to bring the fuel concentration in your vessel now down below a certain, that OFSFC level before you can bring in air. And then once you've done that, once the welder have done their job and you've kept them safe, then you need to also make sure that the filling process is done safely, because you saw what happened at Barton Solvent's facility, right, where the one tank exploded during the filling process, right, because they had let air into the tanks, and that destroyed the whole tank farm. Right. So what we can do, and what we're going to look at in chapter 7 here, is to do purging. Right. So you have your high pressure here would be, if you do vacuum purging, would be atmospheric pressure, or whatever your tank is at, and it's probably atmospheric at that if you're only doing vacuum, right? Then what you do, you pump it out to whatever low pressure you have, whatever ultimate pressure of your pump. Right? So in this case, your oxygen concentration stays constant, but you're decreasing, right? You're decreasing the pressure, so you decrease the total number of moles of oxygen in that. So when you, in the next case here, let nitrogen, pure nitrogen, let's assume that first, into the system, right? You're now lowering, you're keeping the number of moles of oxygen constant, but you're increasing the pressure again, so that the total, the fractions changes, right? To look at this, what we're going to assume is that we have pure nitrogen available first, which you probably won't have. So we're going to look at that as the second. What happens? You know, how does this change if you have impure nitrogen? And then what we're going to look at is, just assuming an ideal gas, okay? pump will determine, right, what low pressure you have to work with. And then we're gonna see, so the key here, right, you have a starting concentration, whether it's a fuel concentration that you need to reduce or an oxygen concentration, right, that you need to reduce. And you need to determine how many cycles do I have to do until I'm below the limit. Right, so if we have an ideal gas, right, then we have the total number of moles at high pressure obviously is P high times volume over RT, and the total number of moles at low right, which means that our N low over N high, the total is equal to PL over P high. Okay, so if we start out with our Y0, right, we also have N0 here. If we pump this out, our concentration stays the same, but we're decreasing the number of moles. So the number of moles here changes. If we now introduce pure nitrogen, our number of moles of oxygen stays the same, but we're changing the concentration. Right, so, and if you look at this, our N0 here would be equal to our Y0, the fraction, times NH. And our N0 here is the initial number of moles of oxygen that we had. If you're looking at N1 is our concentration here, times pH. What units we're working in. Right, so here is NY times the total, but it's also equal to Y0 times N low. Right. So if we write Y1 is therefore equal to Y0 NL over, which is equal to Y0 P low over P top. Okay, if we do this again, right, actually we should do it at N2. So N2, same thing, is Y1 N low, which is equal to Y2 N high, and we have Y2 is equal to Y1 PR over PH, and we have Y2 is equal to Y0 P low over PH times 2. Okay, so if we continue doing this, we can see that if we go Yn is equal to Y0, actually I think they're using J in the book. P low over PH to the power of J. So in other words, if you know your pressures, right, your ultimate pressures, if you do vacuum purging, you're probably working with atmospheric up here, and P low is your vacuum, the vacuum that's limited by your pump. And you're trying to take it from Y0, which might be, depending on what you're doing there, right? if we're looking at in-service oxygen concentration, this would likely be air, and you're at 0.21. And then you know here is what we just were talking about. What is the in-service oxygen concentration? That would be the number you have here. And this equation can be used to determine how many cycles you have to do to get it below, to get the oxygen concentration below what you need it to be. That equation can also be used, right, for fuel concentrations. Right, you can use the same equation. You just have to, what is your fuel concentration to start with, right, and what do you need to bring it down to. So the complicating factor here would be now, right, if this equation, what we've been looking at here is assuming that here we're adding pure nitrogen. Because that's N, right, N1 is the same, so that doesn't change the number of moles of oxygen. If you have impure nitrogen, then obviously you're going to increase the number of moles of oxygen here. And so you can't use this equation. So this is equation 7.6. Now before we derive that equation, right, we can imagine that, so this is vacuum purging, which is a good way if obviously you have a pump so that you can actually pump out your system, and your reactor, you have to know what your limits on the reactor is. Do remember that the fact that your reactor can hold a certain amount of pressure doesn't necessarily mean that it can hold a certain amount of vacuum, right? So the limits are a little bit different. For stainless steel, it's probably okay. But so this, when you pull vacuum on something, right, and then you introduce pure nitrogen, then if that pressure, you're not pressurizing nitrogen, you're not using a whole lot of nitrogen. But you're probably limited in your pump. And pumping out is usually taking longer. So the other thing that you can do is pressure purging. So in this case, we just, our P low now, right, in this case, is atmospheric. And instead, right, you're pressurizing it with nitrogen, and then you're letting it out, right? So you can see it's very similar, and you can use the same equation. You just start your Y initial, you just redefine your Y initial so that this is your Y0. And then you can pretend like you're doing vacuum purging. You can use the same equation. It's just that your P height is now above atmospheric, right? Because you're pressurizing your vessel and then letting it back out to atmospheric. But you can use the same equation. You just redefine your Y0 value. And then of course, depending on what you have access to, you can do combined vacuum and pressure purging. So it's what you do is going to be dependent on what equipment you have access to, and how expensive your nitrogen is, right? Because pressure purging, as you can imagine, requires a lot more nitrogen. If you have compressing it, you're using a lot higher number of moles of nitrogen. Yes? Well, you still have to, right? The problem is you need pure nitrogen. So air separators are still a pretty significant fraction of cost. You know, it's not a huge amount, but it depends on, it depends on how much you need to use and what you have access to at your plant. It's true that, right, it's already 79%, but, you know, the problem is the other 21% is oxygen, right? And that's what we want to avoid. So we do need some kind of air separator, and, you know, that can be costly. Especially if you, I mean, if you're buying your nitrogen in gas cylinders, then you probably want to avoid as much of that as possible. So, right. So if you we can call this B atmospheric, and you can go one step further, right, where you go, you pressurize, and then you pull vacuum on it, right? And if you do that, you can decide to do pressurized first, or you can decide to pull vacuum first. But that it's more realistic that you're just doing one. And probably the most common, if you do have access to nitrogen, is probably pressurizing, because it's faster. Right? You're limited by how fast you can pull vacuum on your cylinder. Okay, so, but let's look at how all of this changes now if you're using impure nitrogen. Okay, so what we're gonna look at is trying to reduce the oxygen concentration to whatever we determine was our in-service oxygen concentration. So we need to reduce it from our Y equals 0.21, but now we have the added complication that our N2 contains a fraction of oxygen. I think that's what oxo is what they used in the book. I kind of like to put Y N2, one Y O N2, right? So that you know it's that doesn't really, that's not that important to me. But if you say oxygen in nitrogen, right? As long as you can keep track of it. Okay, so what do we have? So in this case, this stays the same, right? We start with M0, and this one doesn't change, but now, right, the number of moles of oxygen here does not stay the same, because we are adding impure N2. So our N2 has a fraction of oxygen in it. Right, so our N12 is equal to our N1, which is the number of moles of oxygen here, plus the NON2, whatever oxygen, whatever number of moles of oxygen we added with the nitrogen. So N1 is equal to our Y0 times N low, which is a total, which is Y0, and P low V over RT. Okay, so how much oxygen did we add?